We humans are made up of trillions of cells, which can be broken down into molecules, then atoms, and then protons, electrons, and neutrons. Even smaller are particles called quarks. But what are these made up of? Over decades of research, scientists have proposed a possible answer: string theory. To understand string theory, we must be aware that protons and neutrons are made up of elementary particles, the most fundamental particles of the universe. Quarks are a type of elementary particle, but what if we go even smaller? This is where string theory comes into play. String theory theorizes that if we zoom far enough into any particle, like a quark, we will find a loop of one of these one-dimensional strings. Harvard physicist Brian Greene describes strings as little filaments of vibrating energy. All distinct strings have unique frequencies and shapes. To illustrate, think of a guitar. Similar to how each chord produces a distinct sound, one string might produce a quark, while another might produce an electron. So what happens if you were to take one of these one-dimensional strings and stretch it out into multiple dimensions? You would create a membrane, otherwise known as a D2 brane. Our universe exists on a brane, while our multiverse is composed of various branes placed next to each other. To illustrate the multiverse, imagine a deck of cards. Now imagine that we take one card. This is the brane where our universe is located. Right next to this are other parallel universes on separate branes. Interestingly, in relation to branes, some physicists have proposed the ekpyrotic universe theory, which suggests that a possible cause of the Big Bang could have been a collision of two consecutive branes. These events have already happened several times and could possibly happen again in the future. So has string theory been tested? Unfortunately, there has been no evidence that fully confirms string theory due to the limitations of particle accelerators, which are machines that collide charged particles at speeds up to 99% of the speed of light. Even so, Stanford physicist Stephen Gubser mentions that particle accelerators still have to be 100 trillion times more powerful to directly observe signs of string theory. Although string theory remains an incomplete theory, many scientists refuse to give up on it due to the possibility of uniting the theories of quantum mechanics and Einstein's general relativity. To put it simply, general relativity concerns large-scale physics, like black holes, while quantum mechanics concerns small-scale physics, like quarks. But they contradict each other when placed at similar scales. String theory could unite these two theories, which could be revolutionary to theoretical physics and explain space phenomena like black holes and wormholes. As humans, we live in a beautifully chaotic universe that we are still trying to comprehend. Dealing with the minuscule nature of quarks to the enormity of the multiverse, string theory provides a foundation for understanding the complex world around us. If proven, string theory could truly be the theory of everything.